Hello, keen and excited Year 11 students. Sorry I can't be with you today, but this is the best that we can do, so enjoy this lesson on similar triangles. Okay, now let's get into the lesson for today. Now, last class on Friday we dealt with congruent triangles, and today we're dealing with similar triangles. And what you need to understand is that even though we learnt in Year 10 that there are 4 tests for congruent triangles and 4 tests for similar triangles, your textbook only really includes 3 tests for similar triangles. So the first test that we're dealing with, side, side, side. It's not the same as congruency. We have to show that the matching or corresponding sides are in the same ratio, and we'll do an example in a moment of that. Side angle side, next one, exactly the same as before, except the sides must be in the same ratio. And finally, if you can show that 3 angles match up with each other, we've got similar triangles. And just recall that 3 vertical lines are our symbols for similarity. So let's deal now with our ratio of intercepts formula. In the past, we've dealt with 2 parallel lines with a transversal. Remember, a transversal is just a line that crosses parallel lines. Now we're going to have more than 2, and when we do that, what we actually get is a few different bits. So I could look at that bit there and think of it as an A, that length there, and think of it as a B. From D to E, I could think of as C, and from E to F, I could think of as D. A bit hard there to write that. But what actually happens then is that when we look at those ratios, we end up with A over B gives the same ratio as C over D. It makes no difference at all. So the textbook will write it as the distance from AB over the distance to BC is equal to the distance from DE over the distance from E to F. Well, that's the same as what I've written there. So just keep that in the back of your mind. Also remember that if we have 2 parallel lines, so let's say we've got 2 parallel lines and 2 transversals, the same rule applies, because where the 2 transversals meet, you can actually draw in another parallel line, and then your rules still apply. A over B equals C over D. And there are some questions like that in the textbook where there's no 3rd parallel line but the transversals meet, so you've actually got to place the 3rd parallel line there. So just keep that in the back of your mind when you get to those sorts of questions. Rightio, here's our first example. Find a pair of similar triangles amongst those shown and give a reason for your answer. Well, the first thing we're going to do is have a bit of a look at the angles. You'll notice that triangle A, triangle B, and triangle C all have an obtuse angle of 135 degrees. So they all match up. Let's look at the shortest known side on each triangle. So let's look at triangle A. The shortest side is 2 centimeters, and we'll compare it to triangle B. So we're going to do a comparison between A and B first. Triangle B, the shortest side is 4 centimeters. So when we're comparing A to B, we can actually look at the following. Let's look at the sides. If I looked at the 2 centimeter side, it would correspond or match up with the 4 centimeter side on triangle B, and that's going to cancel to a half. Now let's look at a different pair of sides. So let's try looking at the longer side that we know on triangle A and the slightly longer side we know on triangle B, 3 and 6. So if we divide those or compare those 2 sides, 3 over 6 also cancels to a half. Well, look at that. They are in the same proportion. So they're in the same proportion. Well, if we've got 2 sides in the same proportion and angle 135 degrees, is common, that means that we can say by SAS, triangle A is similar to triangle B. Now that's a bit messy, but hopefully you get the idea there. We've used the side angle side, and I've shown two sides are in the same proportion when I compare them with each other. Two pairs of sides, I should say, and we've got a common angle between them. So let's try our next one. Example 2 says to prove triangle ABC is similar to triangle EDC. Now we do know that AB is parallel to DE, so we know AB is parallel to DE, so we're going to use that. That's a bit better. Now, I'm looking at this because I've got no side lengths marked at all. I'm actually looking to see if I can use this common rule here, angle, angle, angle. So let's try it. Let's go for an angle that might match up. So if I do this, let's go angle ACB equals, angle ACB is this angle here, equals angle DCE, it's this angle here, and then our reason is because they are vertically opposite. So there's our reasoning. Let's try and find a different angle. Let's try and find a different angle. Let's go for something like this one. Let's go I know we've got parallel lines, so I would say those two angles are equal because I've got alternate angles, a Z shape happening. So angle BAC equals angle CED, and they are alternate. Whoops, now that's not good. Let's just see if we can backtrack that a little bit. Get the spelling right. Now they are alternate since AB is parallel to DE. And let's go for another one. Let's go for something like this one, angle. Now I know those two angles are also alternate. I've got a Z shape, so angle ABC equals angle CDE, and they are alternate since AB is parallel to DE. Okay, so then we can come up with our conclusion, and our conclusion would be something along the lines of this. Therefore, by angle, 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 triangle ABC is similar to triangle EDC. And we've finished our proof. Probably not as neat as I'd like it to be because I'm drawing on my iPad. It's not quite as precise as I'd like it to be, but hopefully you get the idea. Right, let's progress to our next example. So we go to example 3. Now, for example 3, it says to find the value of the pronumeral. Now, with these shapes, if I look at them, I can see that they are parallel. Not parallel. I can see they're similar. The reason I know they're similar is because I've got 3 equal angles. Remember, if you know 2 angles in a triangle are the same, that means that the remaining angles must also be the same. So because I know they're similar, I'm not going to prove that because we've already done questions of that, but if they're similar, I can find side lengths. If I look on the small triangle, the side I'm looking for is A. Now, which side on the larger triangle corresponds or matches with A? And if I look down here, I can see that they're going to be the 18. So A over 18 equals. Now A came from the smaller triangle, so if I'm looking for another side on the smaller triangle, I've got an 8. So it'd be 8 over 8 would correspond or match up with 14. So now I've got myself an equation, and with an equation like this, I can times both sides by 18, and if I do that, they cancel out, which means I'm now left with A equals, and you just do 8 times 18 over 14 on your calculator, or 8 over 14 times 18, it gives you the same thing, and you'll end up with 72 over 7, or you'll end up with 10 and 2/7 if you'd rather write it as a mixed fraction, or you'll end up with 10.3 if you take it to 1 decimal place. And I suggest don't round to decimal places unless you are asked to. Probably 10 and 2/7 would be my preferred answer, because 72 over 7, whilst correct, it's a bit hard to gauge the size compared to other side lengths. So that's how we would do questions like that one there. Let's try example 3 part B. Now with 3 part B, there's 2 triangles, but one triangle is inside the other, so I'm going to redraw them. That's the easiest way, I think, to do a question like this. So I'm going to draw my little triangle. If I look at the little triangle, that's 9, and the bottom side is 15. Now I'm going to draw the bigger triangle, and we've got a 16 along the top left-hand side, and the bottom length is not C, it's actually C plus 15, which makes it a bit trickier. So let's use our knowledge of similar triangles. If I look at my 2 triangles as I've drawn them, the 2 red ones, C plus 15 is one of the lengths. What does that match up with or correspond with on the smaller triangle? So the C plus 15 corresponds or matches up with the 15. So C plus 15 over 15 equals. Now on the C plus 15 triangle, the other side that I haven't yet used is 16, and it matches up with 9. So I'm going to go equals 16 over 9. Now if we look at this, you'll see that the C plus 15 and the 16 both come from the same triangle. And you'll also notice that if you're looking at that, that something like the, let's just change this color a bit. That's a bit interesting. So something like the 15 and the 9 both come from the smaller triangle. So the 2 top numbers come from one triangle, the 2 bottom numbers come from another triangle. So you just need to remember that, because if you get the order wrong, that can mean your questions end up incorrect. Let's try looking at this now, and we can see that if we times both sides by 15, we'll get rid of the fraction. The other way you could do it is cross multiply, but if I times by 15, that will take place where the 15 will cancel on my left hand side. That leaves me with C plus 15 equals, so on your calculator, 16 over 9 times 15, or 16 times 15 over 9, and you'll end up with 80 over 3, but I'm not going to write it as 80 over 3, I'm going to write it as 26 and 2/3, because that's what 80 over 3 is. Let's minus 15 to both sides, and if I do 26 and 2/3 minus 15, I will end up with 11 2/3. So C is 11 and 2/3. That's the answer I'm actually after there. Right, let's go on to our next question. Part A says to prove that triangles ABC and ADE are similar. Okay, ABC, there's our smaller triangle. ADE is the bigger triangle, so we're trying to prove that those two triangles are similar to each other. Now the key thing for this question is that I'm given parallel lines. The fact that I'm given parallel lines means that I can go about this question quite easily because I know that these two angles will be the same because I've got parallel lines and they'll be corresponding because I've got a backward F shape there. So I can look for that there. So let's have a look at how we're going to set this out. I'm going to use angle, angle, angle because I've got all my angles here. So angle. Angle ACB equals angle AED. So ACB we've got there, AED we've got there, and they are equal because they are corresponding. And why are they corresponding? Because BC is parallel to DE. Let's try another angle. Similarly, I can come across to the left-hand side. Angle ABC equals angle ADE. And why? Well, we know they're corresponding because BC is parallel to DE. And the last angle, angle BAC equals angle DAE because it's a common angle in both triangles. You can see BAC, DAE, they both end up there, so that's a common angle. So we can finish by saying by angle, 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 triangle ABC is similar to triangle ADE. But the next part that we need to consider is part B. It says, hence, find the value of y to 1 decimal place. So I'm going to need a bit more room here, so let me erase what I've done. I know they're similar, so I'm going to erase this information here. Let's do part B and find the value of y to 1 decimal place. Before I do that, I don't have to do this, but if I draw each triangle separately, it might make it easier to visualize or to see the lengths. So there's my smaller triangle. Let's go for the larger triangle. This is ADE. Now the distance from D to E is y, which is what we're looking for. The distance from A to E is 2.4 plus 1.9, which is 4.3. So we end up with something that is probably a little more apparent. Might be easier if it's not so messy, but hopefully you get the idea. Let's look at my larger triangle ADE at the bottom of my screen. The side I'm looking for is y. Y goes along the bottom of my triangle and it matches up with BC. So when I look at that, y will be over 3.7. Let's go to my larger triangle now, and A to E, 4.3, will match up with 2.4. So I end up with 4.3 over 0.4. Now it's just a case of looking at both sides and times them by 3.7. If I do that, 3.7's cancel, and that leaves me with an answer that I can put into the calculator, 4.3 over 2.2. Where did I get 2.2 from? Let's just correct that. You're probably wondering what was going on. That should be a 2.4 because it matches up with 2.4. So let's do that again. 4.3 over 2.4 times 3.7. Put that into the calculator and you'll end up to one decimal place, which is what the question asks, of 6.6. And there's the answer to example 4. Now example number 5. Okay, with this question we have to prove XYZ, triangle XYZ, is similar to triangle WVZ. So we're proving our triangle at the top and our triangle at the bottom are similar. So let's use or compare some matching or corresponding sides. So if I go and match some corresponding sides, if I look on YZ, shorter side is 6. If I look on triangle XYZ, if I look at triangle WVZ, the shorter side is 14. So let's compare those. 6 over 14. If I divide them, they'll cancel to 3/7. Let's look at another side now. Let's look at the slightly longer side on triangle XYZ versus the longer side on triangle WVZ. And that will be 15 matches up or corresponds with 35. And if I cancel that down, 5 goes into 15 3 times, 5 goes into 35 7 times. Both sides cancel down and end up with the same proportion. They're in the same ratio, if you like. So the same proportion. Do we know any angles? I know the included angle because they're vertically opposite. So angle XZY equals angle WZV. And the reason? Because they are vertically opposite. We have to give our reason, remember. So by side angle side, triangle XYZ is similar to triangle WVZ or Z. And there we have example 5. Let's progress to example 6. Oh, this is a ratio of intercepts one. Now you may or may not remember that it's going to be, when you're looking at your transversals, it's the shorter length over the longer length, so x over 8.9 equals shorter length over longer length, 1.5 over 9.3. If we solve that, that's as simple as just going timesing 8.9 to both sides, multiply both sides by 8.9, we end up with our answer, which is, put on the calculator, 1.5 over 9.3 times 8.9, and you'll end up with 1.435483871, but the question says to 3 significant figures, so I'm going to write it only to 3 significant figures, 1.44 to 3 significant figures. So look at the answer on your calculator screen. Well, it would have been this. And the first 3 figures that are significant, 1.43, but the next one's a 5, so it bumps it up to 1.44. And there is example number 6. Let's go on to our final example, example 7. Oh, more transversals, triangles. How are we going to deal with this one? We can use similar triangles or we can use transversals with a parallel line here. I want to use similar triangles. Let's find y first. Using y, I can look at the big triangle and compare that to the smaller triangle, which is this one here. And they're the ones I'm going to do. I'm not going to draw them. I'm going to see if you can actually just follow along with me talking about how we're going to deal with these. So let's just clear that stuff off the screen. On the big triangle, the side along the bottom is a y. It matches up with, on the smaller triangle, 7.1, because it's the side length along the bottom. They're both the parallel sides. On the big triangle, this full length down this side here is 2.7 plus 3.4, which is 6.1. On the smaller triangle, the length down the left-hand side is 3.4. So multiply both sides by 7.1 and you'll end up with your answer, which, if I round to one decimal place, will be 12.7, I hope. So there is y found to one decimal place. Now x is a bit trickier to find. X is a bit trickier to find because I could go down this track. Now, this is not the way I'm going to do it. I'm going to erase something, but I could do this. I could draw two triangles and I could say 5.8, 7.1, 3.4. This distance is y, which I know is 12.7 now. This one's x plus 5.8. This one's 2.7 plus 3.4. And I could start doing like x plus 5.8 over 5.8 equals 7.1 over 3.4. And that would all work perfectly. But I don't want to do that. What I actually want to do is use a bit of a shortcut approach to this I can get away with because I've got parallel lines. So let's have a look at what I'm going to do here. So I'm going to put in a parallel line going across here. So that's like a parallel line going there. And if that's the case, then this length over this length, x over 5.8, is equal to this length over this length, because it's a ratio of intercepts, so 2.7 over 3.4. So into your calculator, you will put 2.7 over 3.4, times it by 5.8, and you end up with, to one decimal place, the answer of 4.6. So that was a whole lot faster than using triangles, using our ratio of intercepts formula. It doesn't matter which way you do it. This is a faster way, but personal preference is what you can go with. It's now time for you to do some questions. So have a lot of fun, and you won't be able to do all of these questions, so just do a selected few. You won't have the time to do all 1 to 15. There's another video for the next period. Go as quickly as you can now.